Now we want to look at how we get the chord of contact of an ellipse. Now this is pretty similar to what we did with the parabola in extension 1. So the idea is that the chord of contact of an ellipse, we've got two tangents that go from the ellipse. So point P, which is x1, y1, and Q is x2, y2. And then T, there is the point where they intersect. So it's x0, y0. So if we have a look at that, the equation of PT would be xx1 on a squared plus yy1 on b squared is equal to 1. Now we know that from what we did with the work with the tangent. So we know that would be the equation there. So we know that if that's the case then, and we've sort of skipped a little bit here, if we have a look over the page, we go and have a look at the equation of QT would be the same, xx2 on a squared plus yy2 on b squared is equal to 1. Now, when we have a look at that, and we set, again, if we subbed x0 into both of those, so we get the x, technically if we subbed the point P, we'd get the x1 and y1, x0, y0, and here when we go with the same thing, we get the substitution, we get the x2, x0, y2, y0, because when we do the substitution of the point of x1, x0 and y0 into the tangent for PT, because it satisfies it, because it's on T satisfies that equation. The same for Q. So T and Q both lie on that line. Now again, when we look at that, we have to look at what's common. When we see the commonality between these two, really we could have a line where we've got down here the xx0 on a squared plus y0 on b squared, where both x1 and y1 can satisfy, and x2, y2 satisfy that one equation. And if that's the case, then that must be a line, because it's only x and y, that goes between x1, y1 and x2, y2, which means that would be the chord of contact. So it's very similar to what we did in the extension 1 course with the parabola, but the idea is that we get the two tangents, and because t0, y0 satisfies both those tangents, so that's we are able to get an equation where both P and Q satisfy that same one equation, and that's an equation of a line that includes x0, y0. So that must mean that's a line between the 2 points P and Q. Again, keep having a look at it. Like, hopefully you get the concept. It's not an easy one, I think, and it baffles students for a while before they get that idea that, well, really we can get we arrange it so we get an equation that includes x0, y0, but satisfies P and Q, which means P and Q must be on that one equational line, and that would be that line there, so that chord of of contact there. So that's how we get that chord of contact. Now, we're going to use that in other problems. If we have a look here about that point T, for a special situation here, if the point T is on the directrix, so we get the idea it's a focal chord, similar to what we had in the extension 1 with the parabola. So the same idea. So if it is on the directrix, x would be A on E. So if that's the case, we sub in A on E, x on A squared, and we get the y times y0 b squared. So we have that. We have the value of x0, and we get x on AE, and we can solve there. That we can solve that because if it's on the if we sub in AE, which is the focal x value of the focal point, we do get a cancellation there. We get y times y0 on b squared is equal to 0 because the ones will cancel, which means that y0 is equal to 0, which means that we get a point of AE 0, which satisfies this equation as it stands when x0 is equal to A on E. So there we go. That's how we were able to say, well, it must be a focal chord because it goes through the focus. Only if x0 is equal to A on E. It didn't matter what y was. So there's how we are. How it didn't matter what y0 was, because as long as it's on that directrix, y0 has no effect on it. So there's another little concept that we need to remember and be able to prove. It's not too hard. Sub in x0 is equal to a on e, and then be able to get a form for the equation. Sub in a on e and get y is equal to 0. So it proves that it goes. The focus satisfies that equation in that form. So there's all the results we need to remember for the ellipse. The equation, the how do we get the eccentricity in either form? So like we've got it there, but remember that e squared is equal to 1 minus the b squared on a squared. And we can, and remember that we can get that manipulation around. So we get the b squared is equal to a squared outside of 1 minus e squared. So we have all that manipulation that we can do. And that's assuming that a is greater than b. In this case, if b is greater than a, we swap all these around. And the foci would swap around as well. So this is when the major axis is on the x-axis. But if it's on the y-axis, it's plus or minus BE. And the rectrices, if the major axis is on the x-axis, if it's on the y-axis, plus or minus B on E. So tangents to ellipse, there's our equations. You need to be able to find the equations, and we haven't written the normal to the ellipse down, but you should be able to find the tangents and normals to the ellipse. Very similar to what you've done with parabolas, all the other types of curves. So the same idea, it just takes a little bit of manipulation to get into these forms. The chord of contact, as we just did, the x0x on a squared, y0y on b squared is equal to 1. And other results that you'll see, and we'll do these as a number of problems as you go through. The sum of distance of the foci to the point on the ellipse is a constant 2a. The chord of contact from a point on the directrix of the focal chord, which we just did. But we'll see this one in classwork and proofs as we go through. So there we go. There's all the results we need to know and manipulate and put in to solve our problems on ellipse. And the next video will go through some of those problems on the ellipse for us to play around with.